Hi people! Today we're going to talk about models of the atom, sometimes called atomic theory. So this is what the world is made of, and how do we know what that looks like? So we've actually seen atoms now, but barely. So how have we known for like 100 years or more what they actually look like? So we're talking about models of the atom. I don't know if you guys know what models are. You can see here, these are models of the city of Toronto. Here are more models of the city of Toronto. So what do you think a model is? Well, it turns out a model is a representation of something. None of these are the actual city of Toronto, but they all represent something about it. So some of these are wrong, the really old one. Some of those streets don't exist anymore. But most of them are right. They just give us different information. So we have lots of different models of the atom, and most of them are right about something and can actually help us learn more about the world. So we've got these different models of the atom, but in general, none of these were created by looking at the atoms. We couldn't look at atoms until very recently. So we used what's called indirect evidence. A good way to think about this is if you look out the window right now, how can you tell if it's windy or not? You can't see wind. Maybe you look for leaves moving on the trees, maybe you look for stuff blowing around on the ground. That's all indirect evidence. You're looking for something that tells you something invisible is there. So, how did it all start? This all started about 2,700 years ago with the Indian sage Kanada. Not Canada, Kanada. And he had this idea that if you kept cutting things, they would get smaller and smaller and smaller until eventually you hit a point where you couldn't break them apart anymore. And so he thought about this with grains of rice. 1 grain of rice is the smallest you can get. Half a grain of rice doesn't count. And so he came up with this idea of these indestructible small pieces of matter. From there, not a lot happened for like 2,000 years, maybe longer, until eventually we got to the 1800s. And this is where we had a big revolution in science. We started doing a lot of experiments, and a bunch of scientists found out more about the atom and thus made new models of what they thought it looked like because they had new evidence. We're going to focus mostly on these three, Thomson, Rutherford, and Bohr, but we need to kind of know how we got there. So we're going to start with the first real model of an atom that had evidence, which is John Dalton. Dalton basically said atoms are spheres. They can't be destroyed, and different elements will look different. So for example, all the atoms of oxygen would look exactly the same, but all the atoms of nitrogen would look different from the oxygen atoms. And he said that atoms can't be created or destroyed. He is still mostly right about everything. Not bad for the 1800s. From here, we had a really interesting experiment with Thomson. And this is one of the models you should know. He came up with a model called the plum pudding model, because he was very British. In America and Canada, I would probably call this the chocolate chip cookie model. He tested atoms by using positive and negative charges. And what he found out was that the atoms tended to be attracted to positive charges. So I don't know if you guys know electricity, but if it's attracted to positive, it's probably negative. So he had this idea that the atom is kind of like a cloud. It's very insubstantial. There's not much in it, but it has these bits of negative charge. So you can see our model here. We've got this positively charged cloud, and we've got these little bits of negative charge in it. After him, Rutherford came along. And Rutherford did what is probably the most famous atomic experiment ever. He called it the gold foil experiment. He basically shot a beam of particles at a very thin piece of gold foil. So kind of one atom thick, although it was probably a bit thicker. And he expected, based on Thomson's model, for a certain something to happen. So take a look here. If Thomson's plum pudding model is correct and most of the atom is just a cloud, if we shoot a bunch of particles at clouds, where would you expect them to go? Take a second and make a guess. So what actually he expected was that they would go straight through. After all, if it's a cloud, if you shoot clouds at other clouds, they just kind of pass right through each other. But it turns out that didn't happen. What actually happened was this. Most of the particles went straight through each other, but every once in a while, one particle banged off in another direction. It got deflected. So if atoms are like clouds, that makes no sense. So Rutherford had to adjust the model based on this new evidence. So, what do you think? How can we explain what atoms look like if every once in a while, when you shoot two atoms together, they bounce off each other? By the way, these guys knew each other. They were friends. Yeah, that's them. Both mustaches. So how did he change the model? Well, Rutherford determined that if every once in a while atoms bounce off each other, there must be some part of the atom that's actually really solid, a very dense area of matter. And so he created the idea of the nucleus. The idea that instead of the atom being a big positive cloud, there's actually a really tiny nugget of positive charge in the middle, and there's still all the negative charges going around it. And so you can see here, all of the particles being shot at the atom, most of them go straight through because they don't hit anything, but that one that hits that nucleus, that dense positive charge, bounces back. So, we've gone through Dalton, atoms are a solid sphere. Thomson, atoms are a positive cloud with negative charges around. Rutherford, who found the nucleus, this area of dense net positive charge right in the middle with still negative charges all around. And Bohr, if you take a look, we call his the planetary model. He just said those negative charges aren't randomly around, they're in shells or orbits, like planets in a solar system. So here you can see, we kind of call this the Bohr-Rutherford model because it's their two ideas together. We've got a dense nucleus in the middle that is positive, and we've got electrons, those negative charges, in orbits around the nucleus. So see if you can fill in this table. We've got our 3 subatomic particles. Subatomic just means smaller than an atom. And where they're located and what their charge is. You'll notice that subatomic particle we didn't talk about yet is the neutron, also found in the nucleus, and it is neutral, which means no charge. The neutron was added later by a guy named Chadwick. Feel free to watch these extra videos that I've linked in the slide deck if you want to learn more about our most recent, most up-to-date model of the atom. Mostly, we're going to use the Bohr-Rutherford model in this class, because that one gives us enough information to predict how elements will behave and what they'll do in chemical reactions. If you're trying to build a quantum supercomputer, though, you need to use the most up-to-date atomic model, which is the electron cloud model, or the quantum model. But in general, this model gives us as much information as we need. Just like a map of Toronto that tells me all the subway stops. If I'm trying to take the subway, that's all I need. I don't need a map that tells me the temperature or the amount of rainfall or the topography. So this model is absolutely correct to a point, but it's correct enough for our purposes in grade 9 and 10 science. So that's all you need to know about how we created a model of the atom, a picture of what we think the atom looks like based on experimental evidence. In the future, we'll start looking at different kinds of elements and exactly what they look like and how they behave.